Morning. Today's lecture is a revision for all what we have taken so far. Maybe this would be part one of our revision, and we would still have another lecture for revision. As you remember, we started with chapter 1, types of foundations. In types of foundation, we took the two major parts of foundations that are shallow foundations and deep foundation. Just description for it. We said that deep foundation consists of driven piles, bored piles, caissons, and shallow foundations includes many other types. We studied mainly the isolated footing as the main type of shallow foundations. Then we studied isolated subjected to normal force and isolated subjected to bending moment also. Then at the end of the course we started to take other types. We studied combined footing, we studied strip footing, and we studied strap footing. Maybe it's not written here, but we studied also strap footing, and it was a very important lecture. But maybe it is not within our scope in the exam. But so far till isolated footings, whether subjected to normal force and or normal force and moment, this is included in our, you should be included in your revision. Just a reminder, this photo was very, you have to keep it in mind. This is exactly what is a foundation. A foundation is a column in the middle and ending up with a bigger pad at the bottom to distribute the load instead of having very high concentrated stress below the column. It is distributed on a larger area. This is the main function of it. Just also another reminder, after I know all types of footings, then I always in my design should go to the cheapest type, the most economic, the safest and most economic. So always the safest and most economic is the isolated footings. Don't prove yourself that you are very very well educated, so you know all types of footings, so you start with deep foundations. No, we always start with isolated footings. This is the cheapest. Why it is the cheapest? Because it only includes bottom reinforcement. It does not include any upper reinforcement. So it is the cheapest. And I can add plain concrete at the bottom to reduce the amount of RC. So it is still going cheaper and cheaper. So isolated footings, if I cannot find a way to use this isolated, then I would go to a case of combined, or a case of a strap, or a case of a strip, or maybe a raft footing, but it will be more expensive. But when I end up, all my trials ended in vain, and I cannot use any of the shallow foundations, then I can go to deep foundations. It will be more expensive, but it will be required. So this is very important. We studied all type, just an introduction for all types of footings, and then we studied all types of, but also an introduction of deep footings, and this was the end of this first lecture. The second lecture we studied shallow foundations in particular, and we took a description of what we are going to do in case we are going to design any shallow foundation. This is the normal procedure. The normal procedure is that I have an RC followed by PC. Just another reminder, whether you put PC or you don't put PC, both are safe, both are stable. There is no effect on the stability. I cannot design something that is not stable. Both are stable, but it is just a matter of economy. Which is more economic? Of course, when I add plain concrete, it is more economic. Why? Because I reduce from the amount of RC. Because if I have a big footing, say that this is the required dimension of the RC in case I don't have plain concrete. If I add this plain concrete, then this design will be reduced. Instead of having these lines here, maybe I would go inside here. This is something that you have to consider, that if I add plain concrete, then my footing is going to be maybe like this. If you don't have plain concrete, then you will go to the upper the dimension. But if you add plain concrete, then your dimension would be reduced, so the price will be reduced. This is one thing we have to take in mind. So we discussed what we are going to do, and we said that we have two codes of practice or two specifications in Egypt, one for the reinforced concrete and one for the soil mechanics. And in our design of the footing, which is the interface between the superstructure and the soil, I have to deal with both. I have to deal first with the code for soil mechanics, so that I would design the dimensions of the footings. What is the length? What is the breadth of the footing? What is the length of the portion that is in contact with the soil? If I am using plain concrete, then this portion will be the plain concrete. If I am not using plain concrete and I'm just putting the minimum, which is maybe 10 centimeters, 15 centimeters, something like this, in this case I don't consider it, I don't see it. I will just see RC as if it is in contact directly with the soil. And when I finish my design, I add plain concrete with a minimum thickness 10 centimeters or something like this. So in this case, I design my footing whichever is in contact with the soil, depending on my assumptions. Am I going to use plain concrete or not? Once I get the dimensions, I go to the reinforced concrete code to design the depth of the footing and calculate the required reinforcement. So first of all, I'm going to calculate the depth of the footing based on the equation that you usually use in the design of any concrete section. Maybe something like this. This is the depth, the required depth of the footing. I design the footing based on all the data I have, the moment, the FCU, and see all the parameters I add. I get the T. Once I get the T, I add the cover, and then I get the D, and then I add the cover to get the T of the RC. Once I reach this, I stop. I don't calculate the steel. Why I don't calculate the steel? Because I need to check shear. I need to check punching. Once I check shear and once and punching, if they are okay, then I will proceed. If they are not okay, then I will need to increase the depth. So that's why I said don't calculate the steel, because if you increase the depth, then the amount of steel will be reduced. So you will have to recalculate it again if you calculate it at the first step. So once I calculate, I check shear and punching. As I said, check of punching is a little bit complicated, so usually it's not the scope of an exam. Maybe check of punching would be okay, but in case I give you, I ask you for a check of shear or a check or even a check of punching, I will give you all the required data. I'm not going to tell you memorize these equations. No, you don't have to memorize any equations. You will just, of course, when I say equation, I mean something complicated, not just load over area. This is not an equation, but if I have something a little with parameters and so on, maybe something like this, I would consider that a very big equation, and I would give it to you, or maybe give you the numbers I require, because I'm not checking you in the exam for mathematical. You study mathematics in a special subject, but in this subject we study geotechnical, so we concentrate on the geotechnical part of our study. Okay, so I'm going to check shear and punching, and as I said, we usually don't see punching in our exams. But even if I ask for shear, or even if I ask for punching, I would give you everything so that you don't have to mathematically calculate things related to this. Then once it is okay for the depth, I get the area of the steel, the required area of steel. Something very important is the comparison between using plain concrete or not using plain concrete. Using plain concrete means plain concrete more than 20 centimeters. Not using plain concrete, it means that I am using it, but it is less than 20 centimeters. So I am putting it as an extra, just to give me a clean environment to work on site. That's all. But it is not included in my calculation. I add it once I finish calculating the RC. I would add a plain concrete all around with a minimum thickness, and that's all. What is a comparison? This table is very important. What are the minimum values? You have to know it by heart if you are an Egyptian engineer. What is the minimum dimension of a footing, length or breadth? It is 80 centimeters. You cannot have a footing less than that. What is the minimum thickness of an RC? It is 40 centimeters. So the minimum footing is 80 by 80, L and B, and 40 in the depth. The minimum amount of steel, this is very important, because the minimum amount of steel, it is either 1.5 D, which is the depth of the footing, or we can just take it 5 phi 12 per meter in each meter, and so on. These are the minimum amounts that we can use in any footing. So in a footing like this, it will be 80 by 80 with a depth of 40. The minimum amount of steel, because this is just 80 centimeter, it would be 4 phi 12 in both directions. This is the minimum footing that you would see in any site or any drawing. Then we started in chapter 3, bearing capacity and settlement. Of course, to design a footing, an isolated footing, I need to know what is the bearing capacity of the soil. We said, very important, that the bearing capacity of the soil consists of two main parts. Of course, before going into the calculation, we discussed how to feel the parameters that are used in this equation. The main parameters are the C and the phi. This was to feel the phi, or the frictional forces of the soil, and this was to feel what is the cohesive forces of the soil, and maybe this was to feel what if I have a soil without any cohesion and without any friction. It would be something like these beads next to each other. They do not have friction to come above each other in this piled shape or this conical shape, and they don't have any cohesion so that they would attract each other and can be reshaped into any shape I would required. So just beads scattered on the ground. So this would be my soil. It is an imaginary soil that does not have any friction or any cohesion. And these are the particles of the soil below under a microscope. Why I'm calculating the bearing capacity? I'm calculating the bearing capacity to prevent something like this, to prevent excessive settlement, to prevent tilting, to prevent distortion of a building. These were examples. We said that to calculate the bearing capacity, I need to calculate two things: the shear failure, the shear capacity of the soil, and this is based on the equations that was given in the Egyptian code, or the equation given in the Egyptian code. Another thing that was added lately to this equation is the effect of settlement, because maybe the structure is standing and it is not falling and it is okay, but the settlement is excessive, and the code has given me that for an isolated footing I have a minimum of 2.5 centimeters of settlement, total settlement. Then I need to calculate the settlement of the footing and ensure that the stress acting on the soil will not induce any settlement more than 2.5 centimeters. So I need to calculate the failure of the footing first, based on the shear failure. And as we said in some of our lectures, that previously, to calculate any design case, I did not have computers, I did not have equations. The only thing I can do is to assume a failure shape and then calculate this case of failure to check the factor of safety. This is how they usually design any case, and this we used in the design of isolated footing here, this case, the bearing capacity, and in the design of retaining walls, we also assume the failure that would happen, and in the maybe design of slope stability, we assume the failure shape and then check the factor of safety. I mean, calculate the ultimate and take a factor of safety to know what is the safe zone. So this is how they previously assumed that a footing would reach failure. The area below the footing, this triangle will move down, pushing these two triangles to the sides, and these two triangles pushed to the sides push the other triangles up above, and so on. So that's why when you see a footing pressing the soil, you find some kind of heave around the footing. This heave is because soil is pushed this way and all the way up, and so on here. So this is how they calculate. But to reach this shape, it means the soil is strong. But if I have weaker soil, then maybe this triangle will push the other triangle and the force will diminish and nothing will move after that. So this was the general shear failure, this is the local shear failure, and this is the weakest type. It's called the punching shear failure, where the footing penetrates the soil, pushing this triangle, and nothing else happening in the area around it. This was the base of the equation of Terzaghi. Terzaghi presented the equation that is the base of the equation that is given in the Egyptian code to calculate the bearing capacity of the soil. But as we said, it is based on calculating the bearing capacity, not including the effect of settlement. This is the equation of the Egyptian code. It is more or less similar to the equation of Terzaghi. There are many parameters. In an exam, of course, I'm not going to give you all of these charts to calculate, but I will give you directly what are these parameters. If I tell you we need lambda c, then you will get the value of lambda c, or maybe I would give you this table so that you would choose. It depends on the exam, but you will not exert an effort in searching for tables or so on. It will be straightforward in front of you, because I don't want to waste the time of the exam in either mathematical calculations or looking in charts and something like this. It is just giving you mainly the numbers, and you would substitute and understand. That's why I concentrate on your understanding. If you tell me that you calculated the ultimate capacity of the soil and getting the allowable, and you reach an allowable, you know that normal soil, the allowable capacity would be 1 kilogram per centimeter square, 2, 3, 4. But if you tell me 500 kilogram per centimeter square, it means that you just follow the equations, and if something went wrong, you cannot even write a comment saying that this value is extremely high. In this case, I understand that you have the sense and the geotechnical feeling. This is what is very important for me. So this is how to calculate the bearing capacity of the soil. This is, of course, an important problem that would come in an exam. Calculate the bearing capacity of the footing, whatever the type of the footing, and you calculate the bearing capacity based on the bearing capacity equation and the settlement equations. And of course, when you calculate both, you have to choose. You are an engineer, so you have to tell me which one you are going to use. Is it the bigger value or the smaller value? Of course, it is the smaller value, because if the smaller value is safe for both methods, but the bigger value is safe for only one method. So I need to decide which one to use in my design. This is in case I have many layers. Of course, it may come as a question, but not just a descriptive question, just to describe. If I have many layers and I calculate the bearing capacity just below the footing and it was safe, is it enough? No, it is not enough. It would be enough only in case the other layers are stronger. So if this is okay, the other layers, of course, will be okay, because the stress will diminish as you go below, and in the same time you have stronger layer. But if you have here a strong layer followed by a weak layer, in this case I have to check the bearing capacity here and check the bearing capacity here again, because this is the top of this layer and it is weaker than the above layer. Then I have to check both, and so on. If the other is weaker also, then I have to go, and so on. But of course, I'm not going to ask you in the exam to repeat your calculation 2 or 3 times to show me that you understand, but I may ask you just a normal question, what you do in case you have 2 layers and the below is weaker. Then you have to check both. This is an example for a case of a strip footing. All the data is given here. You just substitute in the equation, calculate the first value based on first allowable value based on what you have calculated and the factor of safety, which is 3. Then you calculate the settlement. Of course, the equation of the settlement, it's not an equation. You've seen here the derivation of the equation. E is the stress over the strain. The stress is load over area. The strain is delta H over H. settlement over the effective depth of the section that I'm going to design. Then ES, I substitute this, ends up with this equation. You have to know it because you need it in your quick calculation. So I need you to memorize this equation. You just substitute in the equation, get the value that corresponds to a settlement of 2.5 centimeters. This is the value that corresponds to 2.5 centimeters, and this was the value that corresponds to the shear. This is 400 and something, this is 100 and something, then from 1 and 2, then this is our design value. And so on. This is another repetition for another type of footing, but the dimension, it's the same type, but the dimension is less. And I meant by this that you understand that when the dimensions of the footings are small, then the effect of shear is more than the effect of settlement. So if I have a very small footing with high load, then probably the shearing failure is my problem. But if I have a big footing, then the settlement with my problem. So this ends up with this chart. The chart that this is an important chart because it gives you the relation between here is the width of the footing and here is the contact stress. This chart was drawn by calculating many cases and always assuming a value for B, which is the breadth of the footing, say 1 meter, and then using this 1 meter, similar to the previous example, using this 1 meter, I get the value that corresponds to the shearing failure, and I get the value that corresponds for the settlement. Here, as you see, the value that corresponds for the settlement is high, and the value that corresponds for the shear failure is low. Then I go to another case, maybe 2 meters. Based on this, I find that the value that corresponds to the settlement is now less, and that for shear has increased, and so on. I calculate for many values till I draw at the end this curve and this line. The area below these intersecting lines is the required area. Anything below here is safe, anything above here is unsafe. Just a minor touch modification. The intersection is at a point. Our soil is not that strict. Of course, I cannot move on this line and then suddenly the soil, the bearing capacity starts to decrease. This is not accepted. What is accepted is that I would change this intersecting point with a small fillet. So this area below this line, this fillet and this curve is the allowable pressure for my footing with any value. So if I have this chart and I tell you my footing is 3 meters, you go to 3 and go up, cut the whatever line you are going. Here is the settlement line, you settlement curve, you cut it in this point, go horizontally, read this value. This value will be directly the allowable contact pressure. So this we do in big projects, and we design lots of cases, and this would be the result of my analysis. Then we started in the chapter 4, isolated footing. We said that we had before shallow foundations. What is the difference between shallow foundations and isolated footings or isolated foundations? The difference is that isolated footing is one of the types of shallow foundations. Shallow foundations is the big group, and this is just a part of this group. It is the isolated footing. What is an isolated footing? It is a footing with just one column, and as we said, it does not have any upper steel, and it is our target in any design. You have to know, of course, we went directly into an example because we already studied this in the chapter for the this chapter, this chapter, shallow foundation. In shallow foundation, we took the whole design of shallow foundation. So now this is an application for an isolated footing subject to a normal force only. And we took this example. Of course, design of isolated footings is very important, subjected to normal force, and this was our example. You have to read it and understand how we do it. Of course, checking shear, we said that we may have check shear, but we will take all the required value, but checking punching, we are not going to take it anyway. This is the check of shear, this is the check of punching, this is for your own info. What is very important is how to draw a footing. I usually find even in some coursework that students, they just make the calculation and they don't draw. It means that you don't understand where is this steel going to be placed, what is the shape of your footing. So you have to show me that you understand. You have to, it's not just to show me. As an engineer, you have to know if you calculate the main steel in one direction, where are you going to put it? If you calculate the secondary steel in the other direction, where are you going to put it, and so on. So the plan and the cross section are very important in any example. Then we started to discuss the footing subjected to normal force and moment. Do we have this case? Yes, we have this case. Suppose this is the leg of a frame and you have a footing below here. This footing, by any means, it needs to be designed, because it will be, here is, suppose here is my footing and this is my footing here. This footing, of course, it is subjected to normal force. Why it is subjected to normal force? It's the normal force coming from the frame. This is a normal force. But as a leg of frame, there may be a moment in this direction or in the other direction, depending on the type of and the loading of the frame. So it is subjected to normal force and a moment. In this case, I have to design this footing. How to design this footing? Of course, it will be a little bit complicated because I have to include the moment in my calculation. So there is some modification I can do in the footing so that I don't have to design the bending moment. This is the case if I have a permanent moment. What is a permanent moment? A permanent moment is a moment in one direction that does not change. It is always there with the same value and it does not change. In this case, I can take it into consideration, and we said this consideration would be, instead of having, this is the CG of the footing, and I was supposed to put my column here around this CG. This CG was shifted, or the CG of the column was shifted this distance. This is the eccentricity. This eccentricity is the shift that I induced. If I shift the column this distance E, and I have here the normal force, which is, say, P, in this case, P or N, in this case, my force will induce a moment on the footing. This moment is going in this direction, something like this. The value of the moment is equal to P multiplied by E. This is the moment caused by the shift. So if my footing was before that subjected to a moment that is equal to any value. Suppose the value of the moment was equal to m. This is the moment that was acting from the earthquake or from the wind or from the leg of the frame, anything. Of course, it cannot be due to earthquake and wind. Why? Because it is not a permanent case. Maybe because it is the footing of a retaining wall, the footing of a leg of frame. In this case, it is subjected to moment, and I have the value of P. Then in this case, I can get exactly the eccentricity. I have the equation P E equal M. I know M, I know P. In this case, I can get the eccentricity. This eccentricity is the value of the shift of the column that would cancel the effect of the moment. And in this case, I would design a normal isolated footing subjected to normal force only. So in this case, I managed to delete the moment and only design based on P. But on what expense? On the expense of shifting the column. But because you've shifted the column, in this case, this cantilever will not be the same as this cantilever. So in this case, I have to calculate this is the only difference between this case and the original case of isolated footing without moment. Because my column is shifted, so the cantilever in this direction is now increased, so the moment here has increased, and I have to calculate it separately and know the amount of this moment, because the reaction of the soil below is the same. It's not going to change because the reaction will be only due to the force P. But the length of the cantilever has changed, so it will be similar to a footing, maybe bigger a little bit, something like this. If I have my footing like this, then it will be the similar case. Anyway, don't consider what I'm saying now, just consider that in case you have a big cantilever like this, you have to design this cantilever and get the value of the moment and get the corresponding amount of steel. Suppose I have a temporary moment. A temporary moment is a moment that changes in direction or in magnitude. In this case, I cannot make a shift. I have to keep the column, because if I make the shift to suit one case, it will not be good for the other case. So the best thing is to keep it in place and design based on having a moment, a permanent, a temporary moment acting. It may go this direction, go into the other direction. I don't know exactly what will happen, so I have to design based on the maximum in both directions. Based on this maximum in both directions, I will have two soil stresses instead of having one similar to the previous cases of normal force only or normal force with permanent moment. I will have something like this, F minimum and F maximum. And this was an example. We took this example. We studied. This is the shape of the shift of the column, and so on till we design the example till the end. What is very important, but not for calculation, but for understanding. This is, as we said, F minimum and F maximum in case of footing subjected to a moment. So it will be a moment like this. If I have a moment like this, this will be the shape in case I have one moment in this direction. How to calculate the stresses on these or the moment on this Z. You remember the Z, which is the distance of the cantilever. Here I don't have this uniform moment. It is a little bit complicated. I have maximum value here and a less value here, so I have to calculate this new moment based on these values. It is complicated and I have to calculate the moment in the other direction, of course it will be also based on this F minimum and F maximum and so on. It is a little bit complicated than the other. Of course, the shape, the reinforcement and everything will be similar to an isolated footing, but what is the difference? The difference is that this reinforcement will be higher in values. The amount of steel will be more than the case of a normal force. Can we have moment in both directions? Yes. Suppose I have permanent moment, but it is this way and this this direction and this direction. Suppose you have something like this. Then in this case you get the resultant, you make a shift based on this moment and you make another shift based on this moment and put the new the dimensions or the new location. Maybe it would be in this location or another location based on the directions of the moments. And in this case I will also continue the previous example without any change, because I'm going to design my footing based on just one normal force, and I will cancel this moment and this moment based on having permanent moment in both directions. But in case I have this case, this temporary case, then I will have I mean, if I don't have this case, if I have permanent, not a permanent moment, a temporary moment, it is changing, then I would have these four values, F1, F2, F3, F4, and maybe one of them or more is negative. It is much, much more complicated. All of this is given in this chart. This is the case of just one moment, either mx or my. This is the case of having mx plus my. This is case of having mx and my, and the result was one of them is negative, or maybe two values were negative or more. In this case, I have to design based on this case. It is a little bit complicated, but you have to understand what are we going to do. Then this ended our discussion for the soil and for the footings. Then we went in chapter 5 for a problematic soil. What is a problematic soil? As a rule of thumb, all soils are problematic. Every soil has a problem. But if this problem is predicted and I can deal with it, then we do not consider it problematic, because I know how to deal with it. But if I have a soil that has a problem and I cannot predict what it is going to do, or the effect of this problematic soil is destructive for the structure, then in this case it is a problematic soil. You have to know what are the types of the normal types of problematic soil that are found in Egypt: expansive soil, collapsible soil, very soft clay soil. These are the three main categories. And we said that there is another additional category, which is the sinkholes, or the rock that have the capacity to collapse, because it includes cavities inside, and it maybe the upper crust of the cavity is not adequate and cannot carry the load, and you would have something like this. Of course, this is in Egypt, but in many other places you may find very big sinkholes, and these sinkholes may take maybe full buildings inside of it. So it is very problematic. So it is a problematic type of rock. Here, don't waste your time in just memorizing where it is found. And I need you to know that it is you have two major types of problematic soil, which is expansive and collapsible. Both are affected by water. They are dry in the current case, and when water reach them, one of them increases inside, which is the swelling or the expansive clay, and the other collapses, which is the collapsible sand or the collapsible soil. So this is what you have to know. And where are they found? They are found in areas that were wet very long time ago, in the desert, maybe like in Shuru, in Obur city, in these areas that used to receive water from the Nile during the flood, but after the flood it did not receive any amount of water. So now when I go to these areas and build my buildings, it will be on top of the soil that was wet very long time ago. Once I start putting my water networks, and I put my gardens, and I start wetting this area, water will come again and will reach the layers that are problematic below the soil for the first time since maybe decades or maybe hundreds of years ago. Maybe it's not only because of our flood. Maybe the river Nile has changed the direction. Maybe a million years ago it was in a place, now it is another place. So it was wet one day and now it is not wet. So once it receives this new amount of water, it starts either to collapse or to increase in size and swell, and this is very important to detect during site investigations. If I have a site investigation, of course in site investigation we use water, so using water may destroy the samples that we get, and it either swells or collapses before I check it. So I need to have a special type of site investigation that is capable of detecting these types of soils. So you need to understand the idea of what is collapsible soil, how to deal with it, how to detect it during site investigation. Of course, you have here lots of shots from the Egyptian code for soil mechanics, just to get familiar with it in case you use it in the future. How to get it using some field tests like SPT, plate loading test, and so on. Try to understand. I'm not asking you to memorize anything, just understand, because if your answer show that you understand how to deal with whatever type of soil you have, then it is adequate as an answer. The third type, we said that it is very soft soil. What is very important about this soft soil is that you cannot get samples. If I have very soft soil, if I try to get a sample, it will fall from any sampler. So I have to check it on site. The best thing to do is to conduct this vein shear test. Vein shear test is a double plate that is inserted in the soil and then rotated around an axis, and I measure the resistance of the soil to this rotation, this torque that I'm applying. If the resistance is high, then the soil is okay. If the resistance is very low, then the soil is very soft, and so on. And the code give me what are the values that can describe the type of the soil and so on. So this chapter is very important. This photo is also very important because it is the sinkhole in Guatemala, and it shows you that it is extremely big and it can take a full building and maybe lots of lives would be affected in case I have something like this. This is how the sinkhole, the shapes of the sinkhole, and how it starts and how it develops. I may have this shape, just water going through. Again, it is the effect of water on some types of rock that is affected by water. It dissolves the rock. So once it dissolves the rock dissolve and move away. So I have this subsidence in the rock, or I may have a cave and then the upper portion would collapse. I may have here the topsoil would escape. I may have here something like this. Similar, the topsoil is going away, but it is just filling a gap that was because of the effect of the water on the rock first, and then affecting the soil above, and so on. You have lots of cases. By this, I think we can stop here, because now we reached chapter 5, which is the problematic soil. In another lecture, we are going to discuss the deep foundations and the retaining walls. So if I study this, then I would have a full picture of all of our topics that was discussed this semester. Thank you, and see you in the other lecture, inshallah.